Hello, everyone. Sorry, my name's Ina. Thank you very much for the introduction, Nigel. I'm going to be running through primarily I'm going to be running through how finite element methods are used in geotechnics, and I'm then going to go on to how this can be applied in SAFE. So, as a quick run through here, as I mentioned, I wanted to cover finite element theory, and I realize for many of you this is probably quite familiar, but I think you're going to find that it brings out the features of SAFE, and also it's really necessary to understand basic finite element theory to appreciate what the case studies do and show how SAFE has been applied to real-life problems. So, in brief, I'm just going to introduce SAFE. SAFE has been a tool that has been developed within Arab Geotechnics for a long time now, actually. Here's a quick summary of its features in that it does a 2D analysis using quadrilateral elements, which is not the same as all finite element packages out there. It's plane strain, plane stress, or axisymmetric. It calculates displacements, strains, and stresses. It's time dependent, and it can calculate very useful things for geotechnics like time dependent consolidation. We can do calculations in steady state seepage, and it has specific features which are especially good for lab data, for example, like a cyclic loading. We've got special material models such as jointed rock, which really gives SAFE a big advantage. We're able to model soil reinforcement, and because it's been developed over such a long period of time with Arab, we have an extensive number of output options, which a lot of our clients and customers have found extremely useful and pertinent. So as you can see, it's quite a comprehensive program. But I'm just going to go to the basics of finite elements in geotechnics. So this table shows the different types of analysis methods for different types of problems. So as you can see, you've got a limit equilibrium, a limited analysis, a beam spring approach, a full numerical. And as you can see, for the limit equilibrium, limit analysis, and beam spring, we're not able to calculate all these necessary problems. So for example, with stability, you've got wall supports, base heave, and the overall stability. You've got the strut forces, and you've got adjacent structures. So for example, a lot of people might ask, how does FRU compare to SAFE? Well, FRU is a beam spring approach, and in certain cases, for example, it might, although it will give you a good approximation of what's going on in your retaining wall, if you've got an adjacent structure, it doesn't give you information about that adjacent structure. That's where SAFE or a finite element analysis might come in. So it's very good at combining problems. It can also deal with complex loadings, complex soil conditions, in that, for example, it models uses a constitutive model of soil. So you've got nonlinear models of soil as well, and its complex boundary conditions. And the fact that it models time effects and the development of pore pressures is exclusive to finite elements, I think. There's also the case that within finite elements, there is no assumption of a failure mechanism. So there's no failure surface or mode of it. No failure mode is required. So in this case, it's a very powerful tool, and it's very useful for a general geotechnical problem. Now, when is finite element analysis appropriate? Well, if you look at this table here, you've got different solution requirements. And FE is the only type of analysis or method of analysis that meets all those solution requirements. So, for example, a program like FRU with the beam spring approach, you can meet equilibrium compatibility, the boundary conditions as well. But the constitutive behavior of the soil isn't modeled as well as with FE. So the soil is actually modeled as a set of springs as opposed to an FE, where you can really model the soil with special material models, which I'm going to come to very soon. So now we're going to go on to, if you want to set up an FE model, how do you do it? Well, there are 4 major stages. One is the idealisation, and that's what kind of problem do you have? And this leads to how the problem is analysed, and I'm going to touch upon that now. You've also got the discretisation, which is really how the measure is generated. SAFE now has special features such as auto-measuring where you can, and also generally you can import DXFs to make a mesh. So we've tried generally to make the measuring process as easy as possible for the user to do. You've got to decide on the boundary distances and conditions, and this affects in the end how the model behaves. And of course the construction stages, it's very important, and properties in the different construction stages. So if we go into this in detail, there are two major types of idealization that normally come with a geotechnical problem. One of them is plane strain, where the problem is considered to extend infinitely into the page. So this includes tunnels, strip footings, and retaining walls. But say, for example, you had a plane strain problem, you might have some isolated structural elements, such as piles or columns or beams, and they don't necessarily behave in a plane strain way. But they can be included into the model by adjusting the properties to reflect the fact that these elements are not continuous. Worked examples of how this can be done are included in the SAFE manual, which can be downloaded from the website. But it is something that can be done, and can be done, as you can see from this equation, fairly simply. We've also got in here an axisymmetric idealization. So this is another type of idealization which is very common. So for a pile or a circular footing or a casing, and one of our case studies that would follow is going to cover this kind of example. But in brief, for your case in here, for example, you would cut a line in the middle and take the mesh along the axis of symmetry almost. So you can see the mesh, and you can see in this square here how the mesh is particularly taken from this specific problem. So we're going to move on now to discretization, or forming the mesh. So SAFE uses continuing 2D elements only. And I'm going to touch upon this later and really show it in the case studies, but there are advantages to using 2D elements as opposed to 1D elements. We've also got a mesh generation that can be based on imported lines and polylines from a DXF. We've got auto meshing and quite a good graphical interface or mesh setup, which I'm going to show in a video now. But this is a quick example of the kind of meshes that have been used in real life problems. So at the top here, we've got an unstructured mesh for a seepage problem. We've got a structured mesh for a retaining wall, pile or basement problem. And at the bottom, we've got a mixed mesh for a tunnel beneath an excavation. So as you can see, SAFE is, or finite elements in general, are able to model a holistic problem. So with this retaining wall, you can actually model the effect of the retaining wall and the construction sequence and the props on the pile close by, on the basement close by. And say, for example, what do you do if you decide to put an excavation nearby? You can model that too. So it's quite a powerful tool, and it helps you understand the holistic problem. So I'm just going to give you a demonstration now of setting up a mesh. So you can see it's something very similar to CAD. We've got crosshairs here which help us actually set up the lines. And I'm just here drawing the square. And this square could represent a specific soil layer. It could represent something, for example, where within the square we could draw a retaining wall, or we could apply some loads on top of the square. So once we've assigned properties, as you'll see, we can assign a lot of other things. Now, I've gone to adding a node, and the reason I'm going to add a node is that maybe, for example, I want to put a displacement point in a certain place, or something along those lines. I might need to put that node in. And by adding a node, I can actually refine my mesh, which is going to come up soon. So you select all the elements and you define an area. In this case, we've only got one material, but I could draw extra boxes for more materials and apply more materials, or I can choose specific elements within and change the materials. Now, in this specific case, you can choose constant mesh, but SAFE enables us to vary the mesh to reduce the element size difference. Anyone who does finite element analysis will know that the measuring process is very important for the accuracy of the results, and this will increase the accuracy of the results. And as you can see, the element is actually concentrated around the node. So that will help us, for example, if we were going to apply a load at that point. So if I now go on to select the nodes, you'll see the kind of options the interface allows for you. So you can apply restraints, you can apply displacements or springs or line loads or even seepage restraints. So it's very easy to define your problem on the basis of your node. We can also choose the line and we can restrain in the X or Y direction appropriately. You can see there. We can also select elements. So I've selected specific elements within the problem here. And you can modify the properties, the material or the group accordingly. So there you go. That's a good example of how SAFE works and how the mesh generation process works. So I'm going to run on now to another element of setting up your FE model, and that is the construction stage. So having set up your mesh, you've got to apply properties and conditions according to your stage. So this is a screen within SAFE, which shows the events and runs, which help you set up a stage construction. And SAFE enables you to do that in the following way, in that the events represent the physical sequence of a stage being modeled, and the runs are the units in which the data is prepared and analyzed, and may be subdivided into a number of increments. So as you can see, the stage construction feature really helps you understand the problem and set up a suitable problem. So just to run through how you would set up the measure, how the mesh connects to the runs. All the models start from run 1. The mesh is constant throughout, and each run is copied from a previous one and edited. But you can actually navigate between the runs using this toolbar here. And once you've navigated between the runs, you can add your loads, you can change your material properties, you can add props, change your water or your boundary conditions accordingly. So there are lots of options with construction stages. Now, one of the major features of SAFE, we feel, is that its material models are extensive. Generally, people do use the elastic Moore-Coulomb model for soils. But in London recently, we've extensively used soil models such as the brick model. So we're constantly also working with research institutions to produce soil models and update our current models. So we've got some research going on with brick. But we find that, for example, elastic Moore-Coulomb can model a lot of things much in an advanced way, such as dilation and the incremental strength increase or decrease. But brick goes that step further in modeling the strain history. So in Oasys and in connection with the work we've done with Arab, we really understand the importance of having well-documented and verified soil models for geotechnical design. And that's why we worked on these models and put together models such as the jointed rock model, because we really don't want the program to be a black box. We want our engineers and the people who are using our software to understand what's going on behind the scenes, really. Now, SAFE is able to model undrained soil conditions, and this is just a quick example of a quick outline of how SAFE models the undrained soil conditions. But a lot of detail for SAFE and the methodology behind SAFE can actually be found in the help manual, which is on our website and can be downloaded. And here's a quick example of how we can find out more about undrained behavior specifically. But if you look on your left-hand side, you'll see that there's you can find out a lot about the theory behind SAFE and how it works from our online help module. Another feature that I've touched upon is consolidation and the consolidation feature within SAFE. Now, SAFE can model time-dependent consolidation, and you can apply changes within time, step or ramp changes to your fixed head boundaries, for example. So this really helps with construction stages where, for example, you want to delay things or shorten things, where you want to look at the impact of your sequence or time sequence. You know, this is quite a helpful tool in that. And SAFE also has the kind of usual features of standard finite element programs, in that, you know, you've got contouring options. You can decide your contours. It's excuse me, and you've got the features of very good outputs that you can present in your reports. As you can see, you've got a graph of variables. For example, you could cut a line through your retaining wall, you could cut a line through an arch and plot bending moments, shear forces, thrust, displacements. So all those options are there for it to make for a very useful piece of software. So now we're going to go on to how SAFE is used in industry. And I'm going to start with a problem that, or a job that Arup has been doing using Oasys SAFE. And that's a suction casing design in Hong Kong, but done by the Arup team in Australia. So SAFE is used to assist in the design of an offshore suction casing foundation system. So it's basically for a meteorological mast, which has been proposed to collect wind data for full farm development. And Arup was responsible for assessing the stability under static and storm loading for a suction casing foundation system. And for an offshore meteorological mast. So if you look to your right-hand side, you can see the tripod configuration that the casings are going to go in. This is part of a GSA model. And here you can see the trial suction casing. And this is the measure that was generated in SAFE, which has been annotated to show where the suction casing is, the boundary conditions, and the soils. As you can see along the center, it's, well, as you can see, it's an axisymmetric problem because it's taken along a line of symmetry. And how was SAFE used? Well, SAFE is used to back-analyze overpressure extraction trials for the test casing. So basically the test casing was pushed out immediate following installation and pushed out following 50 days of setup. And SAFE was particularly useful for this kind of problem because of its time-dependent capability. So it was used to model overpressure stages and holding times employed in actual push-out tests. So in that way, SAFE was a very useful tool. It was also used to back-analyze cyclic loading model tests performed within idealized site soils. So this was basically done on a lab test. And the bottom graph shows how SAFE was used to connect the site data and the lab data. Sorry, I wasn't meant to move on there. So if you just have a look here, you can see how the points connect. And once this back analysis was done, SAFE could be used to predict the stability and settlement of the actual foundation system founded in the real site soils. So this here is a quotation from the Arup engineer who used SAFE, and he's basically said that Oasys SAFE allowed successful back analysis of the trial and model test to be performed and extended the results of these calculations to the Insitu casing design. I was speaking to the Arup engineer, and he's currently working on a publication. So unfortunately, I wasn't able to put this on this presentation, but it's been revealed that actually the SAFE predictions match very closely to the site data once the suction casings were installed. So this gives us a lot of confidence in the SAFE results and what SAFE produces. So I'm going to move on to a project that one of our external customers was doing, which is Raisin Foster Associates. And I would really like to thank Raisin Foster Associates for providing this case study. Due to the nature of the project, I'm not able to divulge a location, but I can run through the SAFE analysis. And Raisin Foster needed to examine the stresses within the tunnel section base lab for a cut and cover tunnel. Now, the geometry of the problem and the stratigraphy is shown here. But the interesting thing about using SAFE, and this goes back to your method of analysis, is that it does a ULS, and you're able to do ULS and SLS checks. So, for example, if you were maybe using a limit analysis method, you would only be able to see the ULS behavior in this kind of problem if you were able to model it at all. Whereas with SAFE, you could see how the structure would behave in a ULS and SLS condition. So in terms of the construction sequence, this is the construction sequence. As you can see, we've got our initial conditions. We install the wall. We excavate and put the props in. Due to its time. There's a construction and delay at the formation level with dewatering. So this picks up on one of SAFE's features, and that you can pick up a timed analysis. You've also got the completion of the tunnel segments, the backfilling, and modelling in the SLS and ULS long-term condition. So in terms of the mesh generation, here's the initial mesh with the boundary conditions. And as you put the prop in, you can see how we've basically given the elements within the tunnel area no material properties. We've put the props in, and we've assigned properties to the retaining wall. As we've put the base slab in and completed the tunnel structure and backfilled, we've associated the right properties to the elements. And then here you can see in the long-term condition we've put the piezometric surface in and the loading in. So a lot of things are happening, but SAFE is able to easily model them. And in terms of its outputs, SAFE is able to take various sections through the different problems. But I've just focused on the one here where we've taken sections through the base slab, and we've looked at the bending moments and the shear force at different points in the construction stages. So as you can see, you can plot the graphs out, you can show it to clients or present it in your report. But another thing that SAFE is able to do is that it's able to pick specific displacements and forces at points of interest along the base slab. So, for example, in this case, it was able to pick up the, I think they put a drainage pipe within the base slab, so it was able to pick up the shear force and thrust within that specific point and see how that would impact on the drainage pipe. And here's just another example of the kind of outputs that SAFE produced for the Raisin and Foster example. So here you've got the ULS bearing pressure along the tunnel base slab, and that could be compared with the ultimate bearing pressure. So this case study not only really demonstrates how SAFE could be used by anyone to look at a tunnel problem, it also demonstrates how SAFE can be used to produce a range of outputs which are meaningful, which should give you a really good understanding of how the structure and the geotechnical problem is behaving. So in that way, I think it's quite an effective case study. So now we're going on to an Arup job. It's a different type of project undertaken by Arup, and it's the analysis of an arch structure. Now, I've spoken to the Arup engineers about this, and Arup actually did a comprehensive study to determine the most appropriate software for this kind of problem. They looked at external and internal finite element packages, and SAFE was chosen in this case because SAFE actually deals with 2D plate elements. So you can actually choose the elements to create a line. So instead of, for example, having a beam element where you specify the beam element and that line is where you take the bending moments through, you can choose the elements for the arch and create a line through the arch. And you can choose the bending moment along this line, which is not possible in some finite element packages. So if I go into the problem, you can see that it's quite a complex one. Arup was asked to do a full technical assessment of the arch structure. They did a full finite element modeling of the construction of the arch and full structural assessment of the panels and power foundation. It's a sloping site with a complex geometry. We've got a pile on one side. You've got a wall close by. So it's quite a complicated problem. And so you can see from the 2D plane strain model, you can see that the SAFE model that was produced was quite complex. We've got a number of nodes and elements too. But if I zoom into the specific structural feature, you can see how it's been modeled. So I'm just going to go now through the construction sequence or the construction stages so that you get an understanding of how the model was set up. So we've got the initialization built to existing levels. We've got the installation of the piles, the construction of the arch. We've got the grout footings and fill down slope. We've got the backfill in stages. We've got the construction in situ, further backfill, and the highway loading. So when the engineers first sat down and had a look at this problem, as you can see, something like finite elements is ideal because you have a number of things that you want to look at. your loading is not symmetric. And you also want to look at what's going on within the arch. So for this kind of problem, really, you do need finite elements. It's just which finite element package you choose. So SAFE was able to model the displacements in the soils at different stages of construction. And as you can see, and we've only looked at the final backfill stage, but this shows cumulative displacement. So from the initial stage, what displacement has occurred, and it really shows you how the problem has impacted on our soils. But you could actually pick the displacement at any point, which I'm going to demonstrate a little bit later on. A lot of outputs were produced for this specific problem, but if you look at this specific output here, you can see that we could actually choose a specific point in the problem. So, for example, if you look at this blue line, it's associated with the left pin cumulative displacement. So it just looks at the left pin, and you can look at how the displacement changes, which starts at initially 0, over all the different construction stages. And you can look at, for example, where does the displacement suddenly drop? How is the displacement affected at certain areas? So it's a very powerful tool for you to understand what's going on in terms of settlement. We're also, for this specific arch problem, or even if you're looking at a tunnel or any kind of structural problem where you've got loading which is not symmetric, you can really get a good understanding of the stresses and see what's happening with the stresses inside the arch. So in this case, for example, you can see how as your loading or your backfill is not symmetric, the stresses in the arch change and how they change, and also what the difference is of installing the cross stitch here. So if you look at the bottom bit here, what's the difference when you have, if you look at the very big difference in stretches here and here, you can see the impact of installing the cross stitch. And the engineer can really get an understanding of the impact of their construction. So this output is another output and another advantage of SAFE that I touched upon, and one of the main reasons why the Arab engineers chose SAFE, in that if you look at the bottom x-axis in rather small writing, you'll see distance along arch. Now, this basically means that a section was taken, so if I just go back up, a section was taken along the arch. So instead of a section just taken along the line of the pile or just along the base of the arch, the section was taken along the actual arch by selecting the elements and making an axis through. And this enabled us to look at what bending moments are happening along the arch, what thrust forces are happening along the arch. So it's a very useful tool. And as you can see here, we've got this compaction pressure here has made a big difference in the stresses, and something like SAFE and a finite element analysis program will bring out these kind of problems and really help you understand what's going on. So this is just another example of where we've taken a cut along the arch, and this time we're looking at thrusts, and we're looking at thrusts at different construction stages. So again, it's just a continual example. But this is something that is very, very useful for retaining walls. And I think I touched upon it at the start with the features. But for example, here we've taken a section through the pile, and we've looked at the bending moment and the thrust. And this helps us understand the capacity of the pile. So we can look at the ULS capacity. How does it compare with the actual bending moment? What's the stress in concrete? How does it compare with the thrust? So it's quite a powerful tool in helping us understand the problem and the impact of what we're doing, the impact of the construction sequence on the arch. So that neatly moves me on actually to our final case study, which is a project, again, within Arab where SAFE was used. And it's a deep temporary earth retaining structure. So here's just a cross-section of the structure. Seeing that it's a temporary structure, we didn't really do an undrained analysis, but we actually looked at a drained analysis with steady-state seepage and a time-dependent coupled consolidation analysis. And SAFE had the ability of letting us model both. So in that way, it was very useful for this kind of problem. Now, when Arab did this study, they actually used one or two different programs to look at how the programs compare and what the outputs were. And from this kind of program, we found that there were actually very big advantages in using SAFE, and we're hoping to put some publications together on this. But some some geotechnical finite element examples, for example, use 1D elements or beam elements, and beam elements are totally permeable, and interface elements, if used, are totally impermeable. So, for example, if you wanted to put a retaining wall in, that would be an interface element. Now, I've mentioned this a few times, but SAFE uses 2D or solid elements, where you can specify permeability. And I think you'll probably be aware that no wall is completely impermeable. So SAFE models the actual problem much more closely than FE program which might use beam or 1D elements. It also allowed for a much more detailed study of more advanced concepts. So we could look at theta, we could look at the capital dilation, we could look at time stepping. And SAFE also, we found, SAFE used an iterative method to solve couple consolidation analysis. So this iterative method made the analysis slightly longer, but there was a much bigger advantage on the flip side in that it can actually accommodate nonlinear features. So we were able to change water tables. We were able to look at materials reaching suction limits, and we were able to look at permeabilities varying as a function of stress. So it gave us a lot of flexibility in our outputs and the ability to look at much more advanced concepts. So I'm just going to give you a live demonstration of this actual problem that was set up. So this is the file that was set up by the Arab engineers. And this is the initial mesh. If you look at the SAFE here, this is probably interesting for a lot of you in that this is the gateway inputs, and you can have a look at your runs. And I could choose a specific run. Say, for example, I wanted to see the full excavation, so I could choose that run, and that would change what's going on in my mesh here. You can see the prop and everything here. You could also specify materials, so I touched upon this, but say, for example, this is a plane strain problem, but I can make it a plane stress or an axisymmetric problem. I can look at different conditions, the drain, the undrained, the consolidating. So we've got different problems there. I can specify properties for my soil. As I previously mentioned, elastic Moore-Coulomb is popular, but we've also got here, we've got brick, we've got modified cam clay, Duncan and Chang. So there are a number of different types of models here that we could use for the materials. So that'll just give you a quick demonstration of the inputs and how that works. But we're actually very interested here in the outputs and what happens with outputs in SAFE. So as you can see here, I've just plotted cumulative displacements, and I've previously shown you this little toolbar here that my arrow is going over, but it helps you to go through the runs and look at the changes, for example, in displacement. And say I was specifically interested in a displacement at a specific point, if I zoom in here, or if I had a look through the vectors here, you can see how the displacements change. You can see how the seepage velocity might change. So if I zoom in at the base of the retaining wall, I can see how my seepage velocity will change here. I can see what the actual number of seepage velocity is. So say, for example, in terms of numbers, I can pick out displacement, I can pick out the stress. And say, for example, if I want to look at effective stress, I don't need to look at the effective stress in the X option. I can look at it in the Y option, the major principal effective stresses, the shear stresses, the percentage of stress mobilized. Now, a lot of people might say, well, these are bells and whistles. But we found, we found a lot of our Arab engineers who said that these things are extremely necessary to understand that the program is working properly and that the outputs are accurate. And we also allow you to have a look at errors as well. And the pore pressures inside the problem. So as you can see, this quick demonstration shows you how powerful a program like SAFE can be, and it can give you a really good understanding in this very simple case of the kind of problems that are going, the kind of issues that are there within your specific problem. So I'm just going to go back now to my PowerPoint presentation. And I think that's given you a good overview of what SAFE can do through some case studies. I'm just coming to my final slide now. So I've touched upon finite element methods in geotechnics, and that really gives you a good basis as to when you should use a program like SAFE. So through our case studies, you can see how powerful a program like SAFE is, and that it can deal with a large number of problems, and that FE in itself is a superior method in certain kind of problems where complex geometry is involved, where you're trying to look at a holistic problem. So, for example, a tunnel next to a retaining wall. So I've covered those different aspects in this particular webinar. The case studies themselves have shown that SAFE is a comprehensive analysis method. This quick summary here kind of mentions the things that I've already brought upon with the case studies, but in brief, the choice of materials is a very strong advantage in SAFE. It's got well-documented materials, and it's able to draw on a lot of experience to model, for example, the brick model and the jointed rock model. You're able to also offer a wide range of tabular and graphical outputs, which again is due to a lot of experience in using SAFE, and that what's the most useful thing for an engineer, how should it be applied. So, for example, we've tried our best to make this software robust in terms of its outputs and producing applicable things where you can see where your errors might be occurring, where you may need to change your measure and everything else. So in that way, we feel that SAFE is a very strong piece of software, and that's the reason it's been used in these case studies for these specific jobs. We've also tried to draw upon how SAFE is a good piece of analysis in that it uses, for example, 2D elements, and how that compares with other software. So I'm just going to finish with, if you have any further questions, the help manual is downloadable, and you can have a look at the kind of problems there. We can provide step-by-step examples if you'd like to go through SAFE. Please feel free to contact us directly. Feel free to contact me and find out, more about SAFE, more about how it's applicable, more about these case studies even, if they are of interest. I'm just going to pass on to Nigel now and say, if there are any further questions, we're happy to take them, and thank you very much for your time.